Okay, so we're going to look at problem 1.49 or 149 from chapter 1. Again, these problems are the same, but my numbers are randomized. My numbers might be different. I'm using the numbers that I did when I had it in class here, so let me just double check. Make sure that we have everything in the same place. Let's see here, 144. 358. Let me get my copy. Here we go. 149. So a heavy rainstorm dumps 1 centimeter of rain on a city 7 kilometers wide and 9 kilometers long in a 2-hour period. And then so the first question is how many metric tons of water fall into the city, and second question is how many gallons of water is this. So a heavy rainstorm dumps a centimeter of rain on a city 7 kilometers wide and 9 kilometers long in a 2-hour period. So rain falls down and we measure it in a length. If you've ever seen a weather station, they use what's like a graduated cylinder. But instead of saying the volume that's fallen into the cylinder, they say a length. And the reason they do this is the assumption is the rain is falling in an even or uniform amount. In fact, this everywhere. So the opening of the cylinder will determine the surface area covered. And so the height is the only thing that really measures what the rainfall is. And so you have a small graduated cylinder, you measure the volume of it. That volume's unique to the diameter of that cylinder. But if you're thinking of the rain's fallen evenly over a whole area, the depth is the only thing that's really uniquely measurable to the rain. And so, like the lake problem, 1.44, we have a depth that we're looking at. And so this is something that if you haven't worked with weather before, or you haven't seen weather measuring equipment, you have to take the unit that they give you for what it's doing, which is at 1 centimeter. And it's kind of hard to measure a thing of length for rainfall because we know a volume's coming down. And so there's an assumption in this problem, and the assumption is fairly valid. It's a good approximation that the rain is falling evenly everywhere. And so the depth would give you a volume if you knew the area the rain was falling over. So I try to think of it as I have some points here. Some area of land here. Let me get this point here. That's all right. And so we have some part of land, and rain is falling on it. It's doing it evenly all across this. So whatever small section of it that I capture, it's going to fill up a certain depth. But that small section I capture, like a little rain collecting tube, and that'll be the depth. Right? Depth, D. I probably shouldn't have put the variable there, but the depth of the rain that's falling. But we could say that if I collected all of these up, they would all register the same depth. And so that's the assumption we make. But just from a unit standpoint, I have something that is 7 kilometers wide by 9 kilometers long. And then on top of that, I have a depth that's equal to 1 centimeter. So I have the dimensions that are defining a volume. This thin layer of water over this entire area. But metric tons is a mass. And so there's a piece of information about rain and water that's in the book. It's in our conversion sheets, and it gets mentioned a couple times. But that the density of water is 1 gram per cubic centimeter. And so we're going to use this density to calculate what we need to find out. And so the first question is, how many metric tons fell? And we know from looking at the dimensions here, we can get a volume. So density is volume divided by mass. So if I cross multiply, I can get mass times density equals volume. Or the idea that mass equals volume divided by density. And I noticed here when I wrote this, this is actually upside down. Let me fix that. It's because I put it in the form that I was going to convert it to later on, and you'll see that. You can do that sometimes. You'll see that you know where it's going, and so you write down that portion of it. So 1 centimeter cubed per gram. That's better. So let's turn this into finding our mass in metric tons. So my length times width times height will give me a volume. Divide it by my density, and I'll get a mass, and then I'll just want to convert that to metric tons. So my length is 9 kilometers. So 9 times 10 to the third kilometers. Nine times 10 to the third meters. Sorry, I said kilometers. And let's see, we have centimeters on the end, and we want metric tons. So we're going to want everything in meters here. Times 7 times kilometers 10 to the third meters times 1 centimeter, which is 10 to the negative 2 meters, divided by my density, which is the same as multiplying by the reciprocal. 1 gram per centimeter cubed. And I need to now convert gram centimeter cube to meters. So there's 100 centimeters per meter cubed. So here I've made my volume, I've taken my density. Now I'm trying to make my units consistent. So I need this in meters per kilogram, and then I'm going to convert that to metric tons. So 1 kilogram is 1,000 grams, and 1 metric ton is 10 to the third kilograms, or 1,000 kilograms. But both are saying the same thing. So we have a form of conversion set up. These are consistent. Let's look at our units. Meters times meters times meters will give me meter cubed. And this meter cubed will cancel those meter cubed out. So that's good. Right? Meters times meters times meters is meters cubed. Here's a meters cubed. This will become a centimeters cubed, so they will clear. And so I no longer have any volume. I have a mass in grams, but I want that in metric tons. Grams and grams clear each other. Kilograms and kilograms, so metric tons. So my conversion factors have it so that I have the numbers I need. I want to use, for the first part here, I'm going to use my scientific notation. So 9 times 7 is 63. 10 to the third times 10 to the third is 10 to the sixth. Times 10 to the negative 2 is 10 to the fourth. And let's see, the 1,000 times 1,000, or 10 to the third times 10 to the third is 10 to the sixth. Right? Because 1,000 is 10 to the third. So these multiplied together are 10 to the sixth down here. So I'll just write that down here as 10 to the sixth. And 100 is 10 squared. My rule of exponents, that's 10 to the sixth. So these will cancel. And so I'm left with metric tons here. And that's 6.5 times 10 to the fifth metric tons. So my scientific notation really helped out here, because 9 times 7 times 1 is 63, 10 times 3 times 10 to the third, 10 to the third times 10 to the negative 2 is 10 to the fourth. I rewrite this in scientific notation, that's 6.5 times 10 to the fifth. The trick here is if I convert these to scientific notation, so let me do this out here, 100 cubed over 10 cubed times 10 cubed. This is 10 to the sixth upstairs. To the sixth upstairs. And this is 10 to the sixth downstairs. Anything divided by itself is 1. And so this becomes 6.5 times 10 to the fifth metric, or I'm sorry, 6.3. I don't know why I wrote 5. It's one of those evenings, I guess. But 6.3 times 10 to the fifth metric tons. But if we look at our numbers, they were all 1 sig fig. So 6 times 10 to the fifth metric tons. And most of the answers that I saw in Mastering Physics were either 5 or 6, depending on how the numbers multiplied out. Though some people might get different. Really, exponents make this math able to be done in your head. This is an example of what the book calls estimation, where you take a power, a measure to one significant figure towards its power of 10. And in doing that, it makes it so that you don't need a calculator. You don't have much precision in the answer, but to be honest, measuring rainfall over 63 square kilometers is not going to be a precise measurement on that level. And so this is a good order of magnitude calculation to get us where we need to go. Well, that was the first part. The second part of this problem asks us how many gallons of water this was. Well, this was a volume issue. So if we ignore this conversion factor here and don't deal with the mass, this part here was just the volume. So the volume is 6.3 times 10 to the 5th meters cubed. We need to convert that to gallons. Well, 1 liter is 1 times 10 to the negative 3 meters cubed. And 1 gallon is 3.785 liters. I run over to my trusty calculator and I get 2 times 10 to the 8th gallons. This conversion factor here and the metric tons coming out to 1, it is good practice for how your powers of 10 and powers of 10 in SI notation can simplify equations and how you can focus on measure. I would play with different ways. I'm doing this quick using my exponent rules to get me to where I need to go. If you're not seeing the exponent rules, plug it all into the calculator and get a feel for it. This is when we want to play with these numbers and to see what they'll bring for us.